Welcome everybody to this presentation where we're going to be talking a bit about how to tie the knot with AI. So the title of this is how to create everyday value in district heating, also cooling, in general thermal systems and by using artificial intelligence. NODA, where I come from, is a company in Sweden. We work with AI-based energy services for grid operators, building owners and automation companies throughout several countries in Europe. You might not believe this given that last slide where we were not unable to get even a transparent picture to work, but we actually do have a background in computer science and artificial intelligence and data science for energy systems applications. NODA was started or founded already in 2005, so we've been doing this for quite some time here. So it's been quite an interesting ride here now. I'll give the word now to Dirk, and he will continue for a few slides on.
Yes, thank you, Christian, and also welcome from my side. Indeed, I'm Dirk Vanhoudth. I work for VITO, which is the Flemish Institute for Technological Research. We are an independent research institute owned by the Flemish government, in Belgium that is. Currently we have more than 900 employees, a turnover of 185 million euros last year, and we work in a lot of fields. Colleagues of mine are working in sustainable chemistry, in land use, in health, in materials and energy. In energy we do a lot, but one of the things that we research are indeed district heating and cooling networks, and this part of VITO, the energy part of VITO, has joined forces with the energy part of the University of Leuven, with IMEC, which is another research institute, and with the University of Hasselt, and together we formed a collaboration called Energyville. And as you can see on this slide, we have more than 350 people working for our institute right now, of which about 100 PhD students. So the agenda for today. I will talk a little bit more about the drivers of digitalization, and then I will talk about digitalization in energy in general, and then more specifically in digitalization in district heating and cooling networks. And then my colleague Christian takes over again, and he will show you some examples of digitalization in heat networks and cooling networks in practice. So this slide you may know. It's a slide about the Moore's law. And this is the law predicted by Gordon Moore already in 1965. And Gordon Moore was one of the co-founders of Intel, the big company, and it predicted the trend of the amount of transistors on computer chips. And in the beginning it said it would double every 12 months, but then 10 years later, in 1975, he had to correct it a bit, saying that it would be every 24 months that the number of transistors would double on chips. And actually this law has been valid for over 50 years. And it's only in the last decade when the pace of the progress declined a bit, but still it's very impressive that, well, already in 65 he could predict a trend like this. So the number of transistors is increasing, and of course, because this number is increasing, also the computer power is exponentially increasing. Here you see a graph of how the MIPS, which stands for million of instructions per second, how this evolves over time, and you see that computers are getting more and more powerful, and the prediction is that somewhere in the 2020s, even computer power would trespass the power of human brain. And the human brain has about 100 million MIPS. So we're getting there within the coming decades. And of course, as a result, you will see that neural networks and also other IA technologies will become more and more complex, and more possibilities are opening up. So that's one thing. The data processing is getting more and more advanced, but of course, first of all, you need the data. And on this graph, I show the price of sensors, sensors to collect data. And you see that sensors are getting cheaper and cheaper. It's getting easier to measure more and more data as a reasonable cost. You see that in 50 years' time, the price of sensors has decreased by a factor 3 to 4 even. So you will have more and more sensors everywhere. So gathering data is getting more and more easy. Processing data is getting more and more easy, but also transfer of data is gigantically increasing. You see the evolution of internet traffic over the last 2 decades, and you see that from 1979, where we were at 60 petabytes already, we went to 54 petabytes in 2007. So that's a multiplication by 900. And even in the last decade, we multiplied the internet traffic by 20 times. So now we're at 1.1 zettabytes. And this is a very large abstract number, but to give you an idea, it's about the same as transferring 390 megabytes per day per inhabitant of the globe. And for the people here that are still old enough to know floppy disks, this would mean that you transfer every day, every human on the planet on average transfers 270 1.44 megabyte floppy disks every day. So that's quite impressive, especially if you know, for example, that the Apollo 11 mission, which brought us to the moon, only carried 4 kilobytes of RAM data. So what we can say is that gathering, transferring, and process of data is taking giant leaps. And we can conclude that right now we're in what we can call a fourth industrial revolution. We all know the first industrial revolution, which was more or less a mechanical revolution by the introduction of the steam engine. That was at the end of the 18th century. Then there was a second industrial revolution with the assembly line, which was introduced first in the meat packing industry in Chicago, and then later it was also adopted by Henry Ford in the automobile industry. And then there was a third industrial revolution with the introduction of the computers in the second half of the 20th century. And right now we're in the middle of a fourth one, where artificial intelligence, big data, robotics, and so on come into our daily life. So these are more or less the drivers of digitalization in energy. If we currently look at electricity, you see that digitalization is already quite present. About 10 years ago, smart meters got introduced, demand-side management systems got introduced, and that was to enable the evolution from traditional centralized energy production networks to smart grids, where you have multiple small-scale decentralized renewable energy production units like wind and solar photovoltaic panels. And now you see that in the electricity sector, digitalization accounts to about 50 billion euros a year, which is actually more than the global gas power generation. So that is what's currently happening in electricity. Now, question is, what would be the next step in digitalization in energy? And then it's of course very hard to predict the future, but it is likely that we will see the same trend as we see in other sectors of our daily life. You see the last 5 to 10 years, you see the rise of platforms bringing together suppliers and consumers without actually owning infrastructure or assets. If you look at Uber, Uber doesn't own taxis itself, but it's a platform where people meet with potential drivers. The same for Airbnb. They don't own building themselves, but they bring together people, travelers, with people that want to share their house, and so forth. Probably in future, also in electricity, you might see the same, that you will get kind of a platform where you have suppliers and demanders of power without even owning generation or network infrastructure. That's electricity. Now, if you look at district heating, we see that digitalization has not taken off to the same extent. District heating and cooling is in that sense a bit lagging behind in comparison to electricity networks. But the first thing, of course, the first question one should think of is, what makes a heat network a digital heat network? And there we've been studying a bit about this, and so far I haven't seen one univocal definition yet. But apparently to me there are some criteria which you could use to conclude whether or not a network is a digital heat network. Of course, a digital heat network will contain a large number of sensors. That's obvious. But besides the sensors, in my opinion, also automated recording, automated transfer, and automated data storage is one of the criteria. And besides gathering of data, I would say also automated analysis of data is very important to be called a digital heat network. And not only these analyses are used for automatic billing of people, to calculate how much energy they consumed and to send them an invoice, but very important is also, I think, in a digital heat network that digitalization is used to optimize the network operation. And in my opinion, this digitalization in district heating and cooling is it's indispensable in future, because as the people who are aware with district heating and cooling networks here know, we're currently going to a new generation of networks. We call it the fourth generation of networks, where you have much more decentralized sources of energy being coupled to the network, and also the temperature levels of these networks are going down. So you will have more renewable sources, and we will have less heat losses. And this of course means that the networks will become more and more complicated, and that we need more and more advanced control systems. But also it means that there's less space for errors to be made, because we have lower temperatures. We can't afford ourselves to make errors, while we can't make use of those low temperatures. That is the introduction I want to give you, and now I'm going to pass the word again to Christian, who will give you some examples of digitalization in district heating and cooling networks.
Thank you, Dirk. So as we mentioned earlier, a lot of the research and a lot of the development that we're doing now is based on two major Horizon 2020 projects. It's been ongoing for a while. One of them is the STORM project. You have the links here also. You can check them out if you want. The STORM project started in 2015 and ended earlier this year. And the TEMPO project started in 2017 and is still ongoing. And these two projects, they kind of combine into building what we call the intelligent storm controller. And this is based on, because the storm project was the first one, and that was focused very much on the fast processes within a thermal system, so more or less the hydraulic part of everything. Whereas the TEMPO project is more focused on the slower parts, the temperature part. So you combine temperature propagation in network with the very fast process of hydraulics. And you have to be able to control both of these parts because they're just two sides of the same coin. And these two things you need to coordinate in order to build an intelligent controller for district heating system. This is one of the things that separates or differentiates district heating and cooling from the power grid, for example. In the power grid, things are more on and off, basically, whereas you have this more complex duality of fast and slow processes interacting in district heating and cooling. If you look at a system overview of the system that we are developing, and we have the green parts here are the ones that we've developed through mainly in the storm project, whereas the yellow parts are more based on TEMPO, which is ongoing work. And then you can also combine this with the third-party integration on the financial operations. But outside the financial operations, we do have, when we combine storm and TEMPO, we have a platform to optimize this whole system in different ways. And the whole thing is built around the consumers because district heating and cooling system, obviously it's demand driven. So in order to optimize this whole system, you need to optimize or be able to control the demand. And once you can control the demand, everything else follows on top of that. Then you can also look at production supply, so forward temperatures, and how you set the pressure head in the network, all the way out through the distribution to handle narrow section and local peaks throughout the grid. And then you have demand-side management and active energy services at the consumer side, predictive maintenance based on all the data that we gather in the buildings. And then on top of that, you have the return temperature going back into the production. Then you have this whole full chain of an optimization of a total thermal grid. And this continues the system overview. Here we can see it's basically in the square here with the four parts which make up the primary parts of the storm and TEMPO controllers, which is the forecaster, planner, tracker, and then the buildings. And these four parts make up the core of the system because in order to build an intelligent system, you need to know what's going on in the future. I mean, that's one of the basic definitions of an AI system, that be able to forecast what's going to happen in the future. So you have this, we've been doing a lot of work on doing good forecasting, both for the heat demand, obviously, but also the available thermal flexibility, because this is also something that we're using in order to optimize the production and distribution. And based on the forecast, you have the planner. It's not just about knowing what's going to happen. You also want to have a system that can analyze and kind of reason about what it wants to happen. So, and this is what the planner is doing. So the planner will take all the forecasts and think about what is the optimal way to use this situation. And then based on that, we'll create control plans. And this in turn is then sent over to what we call the tracker. And the tracker, the purpose of the tracker is to, as the name implies, to track the control plans. And it does that by distributing control actions among all the connected buildings. And then you have a building agent, or it's basically a software agent in each individual building that can interact with the tracker then to kind of take care of all the control actions. And so you have this system that where the forecaster, plan and tracker, they work on a grid level, taking into account what's going on the production side and all distribution, and then you connect this with the buildings, and they all work together in order to maximize the efficiency of the whole system. If we look at the setup of the grid part of this, there are three basic modules that are working within this controller. One module is focused on handling peak loads, which is an obvious problem in a lot of district heating systems. Peak loads are normally expensive fossil fuel. It's not very good for the environment and so on. So normally you want to get rid of the peak, so peak shedding. You have the base part, which is the biomass, or it can be other production units that you're using. But this is for the majority of all the energy usage in the grid. But this is something, even if it's biomass and so on, or excess heat or things like this, which is good for the environment and rather cheap, it's still something that you want to optimize as much as possible. And then the last part is the service part, and this is what connects to the buildings. And so this is kind of the core of the system. And this can also work with external production optimization. For example, as I mentioned before, the financial parts of the production, including taxes and costs for different fuels and so on. This can be input to these operational optimization. Then. The next step, obviously, because this grid system is an operational demand-side management, but you also, in order to get this system up and running, you do collect a lot of data. And this data is, at this point in time, it's normally primary side data. So this is primary side data from the substations in the district heating grid. So basically heat meter data. And this is a lot of data that's collected. And this is not just used to optimize the current state right here and now, but you can also use it to look at how has the substations been working historically. And based on that, you can draw a lot of conclusions of how to identify and diagnose faults and deviations. Because let me tell you, there's a lot of deviations of faults in substations all over district heating systems. And they are the ones, these faults are the ones that we make it so that we need to keep very high temperatures in a lot of district heating grids. So we can identify these faults and also do something about them. We can then lower the system temperatures. Another very important part of this is that you also want to include the customer, because as I said, it's demand side management. One way to do that is that we can't just do this for the grid operator. The grid operator has to work with their customers. And one way to do that is to provide energy services towards the building owners within the district heating grid. And that's the next part of this system here. So you have a whole color, like a smorgasbord, where you have a different range of modules that you can use to not just optimize production and distribution, but also to help the building owners to save energy, to reduce power demand and return temperatures in the substation. You can also use it as a base for doing more advanced indoor climate control, especially in commercial buildings, where this is quite important. And also, once you have this access to the building substation, you also have the secondary side. And if you combine that with the primary side analytics, then you have a very powerful tool to actually analyze what's going on in a substation. Then it's easy to diagnose and also come up with what's the problem with these substations and how you quantify different actions to do that. So this is kind of an overview of how you can work together with a grid owner with their customers. So you create a kind of a win-win situation. Basically, the whole concept here is based on that the grid operator is normally interested in temperatures and megawatts, whereas the building owners are more worried about megawatt hours or gigajoules. So in this creates the basis for a win-win situation. This one here is just to give you an example of, we're doing a lot of nice pictures and overviews here, but this is actually a picture of what a demand signature of a single building looks like. And this is basically what AI looks like in real life. Because normally in a building you would have, traditionally you could have an energy signature, which is basically one number that kind of defines how this building reacts and how it reacts to outer temperatures. But that's a very static view of things. This is a more dynamic view. So we have self-learning systems that kind of collects all the data from the substations, and over time it builds models of the behavior of the buildings and of the substation itself. And these demand signatures, these response signatures and so on, they are all the basis for everything else that's going on in the optimization of this system here. So this is something, as you can see, it looks a bit, it's not something that a human would come up with a signature like this. It would be very hard to collect and organize this data manually. And this is just one building. Imagine having 100 or 1,000 of these buildings in one grid. It would be very hard to do it manually. And this is where AI comes into play. Another thing here is not just controlling the system in a very smart way. It's also about using the data that you collect. And a lot of people talk about collecting a lot of data, and if we just collect the data, then everything is fine, because then we know everything we need to know. This is not true, because data, for humans, data is very hard to relate to. It's just a lot of numbers. And if you get that, or collect all that data, you get this in an Excel file, for example. It's very hard to look at that. You can imagine the picture I just showed you in the previous slide, looking just at numbers. You can't make ends meet on that. You can't really understand what's going on as a human. However, the machines or the computers, they can understand these things, and they can use this data and refine it, transform it into information. And this is at a higher level of value, but it's still based on the data, obviously, but it's instead of data, it's information. So it's important to understand the difference here. And this information is something that experts at grid operators or larger building owners, they can use. For example, this picture here is a contour map of a substation. So if you're an expert training these things, you can just look at this picture. This actually is hourly data from 4 different values from a substation for a whole heating season. So it's a lot of data here. But if you're training these things, you can just look at this picture and you can realize if it's working good or not so good. And you can also use it as like a visual tool to see if it's what kind of problems you have in a substation. This is information. Then you can take it to the next level by using, for example, neural networks to further refine the information. You can create knowledge based on that. That's like even increase the value even more. And then instead of sending this very, very colorful picture, sending that to the building owner, which might be hard for him or her to understand what's going on, the computer will interpret this picture and create a text, for example, create an analysis based on this. For example, that valve in this particular building is not working properly. That's knowledge. So you can see going from all those numbers in an Excel sheet, from data, going into information, and then going into knowledge. These are 3 different levels of where you increase the value of the data you have. So everything starts with the data, but you need to be aware that you need to refine it into information and further on to knowledge. And then the next step after knowledge is wisdom. However, so far we haven't come up with an algorithm to create wisdom, but we're still working on that. We'll see how that goes. So, and all these things obviously are built into a system that's actually up and running. So it's not just a lot of algorithms. It's all based in a framework that can be used in a grid. And the reason why we want to do that is one important part is for the grid operators to use a tool that creates a bond, tying the knot with their customers through active energy services in different ways. But also for the grid operators, you can use these things for moving the demand in time without actually causing any problems for the building owners or consumers, but you still move the time, the demand in time. And that is obviously for CHP optimization, where you have the spot price market where you want to relate your CHP boilers to. You can load shedding, as I mentioned before, and also balancing the demand and also the return and supply temperature. So you get a more even balance in the system. And if you have lower temperatures and more balanced demand, then it's easier to include renewable sources and excess heat and so on. And this makes a perfect platform for introducing more sustainable energy systems in a city. And this is basically what makes district heating and cooling a very, very suitable backbone for a smart city, because you can combine all these things. You can combine excess heat and everything else that's going on in the city and combine it. This is why we see this as a cornerstone of the future sustainable energy systems throughout Europe here. So thank you very much for